Hey, how's it going?
Good. How about you?
Good, good. Hi, Professor.
Hey, how's it going?
Doing good. How are you?
Good, good.
That's my friend. Am I sitting next to this way?
Yeah.
No, no. There you go.
Point for me, Jack.
I was asleep.
Oh, Jack said he's in the machine shop.
Jackie is older.
Yeah. I can't read. Look at my new shirt.
You just take some like other computers.
I have one for everything except formula. Formula. Do you know what? Do you know what actually does suck? So formula t-shirts were $35. Rover was what, 25? 25. Guess how much Baja t-shirts are?
55.
11.
What?
Isn't that weird? And they have like a crap ton of them.
Oh, it's because they're old, that's fine.
No, they're brand new. They just started in. So I want to know who they're. Yeah, who's their dealer? Because like that's.
Ask
we need
them.
that.
You gotta ask them.
Yeah.
We got it from someone from Rocket.
Rocket, yeah. So Chris's dad's who you're talking about. And Rockets was $20. So it's still more expensive.
George is kidding.
He charges kid more than us. Ours is 20? Yeah. But how was it?
$11.
Yeah, originally it was free, but then he moved it up to one. Because they give the whole team up for free. Yeah, it's not fair at all. Kind of deep. Don't like your mustache.
Don't be jealous.
I could have done that. Actually, have you guys ever seen me a sniper?
What? No.
It's you want to throw up, bro. I did it as a joke for Halloween one year, and I tried to go to school on the very last day of the semester like it. And my parents got really pissed at me. It looks like I should be arrested. Let's see. You'll understand.
All right, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Good. How are you?
Good, good. Thank you for asking. Appreciate it. All right, so the plan for today is we're going to finish up our lecture notes on oscillating rigid flow. Okay, we're about halfway through, and so I think we have no problems finishing today. Remember, the project is due tomorrow evening, and so make sure you guys are working on that. I think I've gotten maybe about 10 submissions so far, and so if you have it done, just go ahead and submit it. But if you're still having trouble finding vessels or whatnot, then please let me know, and I'll do my best to help you out. Okay. It is a little bit late right now, but if you have one of the more difficult image data sets, then it is possible for you to switch. Just let me know if you're really struggling with your image data. Then we can arrange that. Okay. And so, are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And we are covering oscillating flow in rigid vessels. All right. And so the whole idea with this unit here is we are exploring what the velocity profile looks like when our pressure gradients are unsteady. Because the velocity profile is something it's important for our analysis, because if we have the velocity profile, we can compute a lot of really interesting quantities like the wall shear stress, right? And so, you can think of this as kind of almost like an extension over, what you've learned in fluid mechanics. Because in fluid mechanics, you've covered the situation. You've covered the steady case, right? And so under steady conditions, we know that we have a parabolic profile, right? Right. And so when everything's steady and the walls are rigid, that's what we get. Okay. And we were just right at the end of our derivation of what the velocity profile looks like when you're unsteady. Okay. Okay. And the main upshot, or the main conclusion that we got, was that when we are considering unsteady situations, then our velocity profile depends on these Bessel functions. Okay. I guess Bessel is a guy's name, so I should capitalize his name. Okay. All right, and so since we're just at the end, I'm going to go ahead and skip to the final answer, because I think what's more important than kind of the last mathematical details is just examining what this function looks like. Okay. And so in the end, we get the following result. Okay. And so we have uz as a function of r and t. Okay. And so here we have multiple variables here. We have radius and time. We get the following result. So we have a divided by I rho omega. Right? Where omega here, that's the frequency of the oscillations. Okay, so that's important to know. Okay. Remember, we're looking at a purely oscillatory solution, a purely sinusoidal solution. Okay. And the rest of the solution looks like this. We have 1 minus J0. Remember, J0, that's our specialized Bessel function. I to the 3/2 times the radial coordinate times square root of omega over nu. Divided by I to the 3/2 big R square root of omega over nu. Okay. And so if you look back in your notes, we kind of left off right at the point where we were applying our no slip boundary condition. And so this denominator term right here comes directly from that no slip boundary condition. Okay. All right, so that's the spatial component, and then our time component is simply just e to the I omega t, which is our sinusoidal function. Sorry, allergies acting up. All right, so this is a mathematical mess, right? And so let's go ahead and pick this apart, just so we can kind of understand what's going on. Okay. All right, and so the first thing I want to highlight to you guys is that this function here, it's separable, right? And so we have one component here, all of these guys here. What you'll notice here is that all these terms don't have the time variable, right? And so what we could say is that this is the spatial component. Okay. And so the only independent variable that we have there is the radius, right? So everything else in that bracketed component is either a constant or some parameter of the problem, right? So time does not show up. All the time dependence is located here. And so, of course, this is not a function that you can you would be able to plot by hand, but if you plug this into Matlab, you can get the velocity profiles from that. And I did post a very simple Matlab code online that you can run to see what these look like. Okay. But before I show you that, I do want to kind of talk about this function just intuitively, just so that you kind of understand what's going on. Okay. All right. And so, one thing one thing we should highlight here is that, this is our unsteady velocity profile, right? And we kind of built this solution under the pretext or under the assumption that we had some kind of, sinusoidal oscillation, okay? And so what we could say is the unsteadiness comes from and so we're going to say the unsteadiness comes from an oscillation with a fixed frequency omega. And that last part's really important because, when you have an unsteady situation, there's lots of different ways you can be unsteady, right? So the definition of unsteady is just that you're not steady, right? And so you can be kind of unpredictable. And so you could be chaotically unsteady, you could be randomly unsteady, you can be, but here we have kind of a very fixed uniform unsteadiness, okay? And so let's look and see, I said this part right here, this is our spatial component of our velocity profile, right? But what you should see here is that, it doesn't just include the spatial variables, okay? Because look at all of these. Right? We have the frequency show up in all the spatial parts, right? And so what this tells us is that, the spatial distribution is actually affected directly by the frequency. Okay? And so depending on the frequency of your oscillations, that's going to actually affect the spatial realm. Which is fascinating because, usually space and time, we assume that these two components are separate, right? And it's true that, in our solution here, we do still have an e to the I omega t, but that omega kind of bleeds its way or kind of has an influence on the spatial coordinate. Okay? And I think from here, it's kind of easier just to kind of draw what's going on. Okay. And so let's consider two cases. Okay. And so first, let's consider a case when the frequency is low. Okay. And so omega is relatively small. All right. So what do we know? What does a sine and cosine function look like when the frequency is small? Well, it just doesn't repeat as often, right? And so if you have a sine function, with a small frequency, it might look something like this. And so we still have changes in time, right? And so this is sine of omega t. Okay. And so we still have changes in time, but those changes occur very, very slowly. Okay. And so let's look and see what happens to the velocity profile under these conditions. Okay. So here is the velocity profile. And so the x-axis here we'll say is uz. And the y-axis here will be r. So, we're kind of just looking directly into the vessel. Okay. And so this is nice that I have different colors. Okay. And so when you have low frequencies like this, you don't actually expect to see that much change, right? And so if you have low frequency, you can kind of almost say that the situation is steady. because what is a steady case other than when your frequency is 0, right? If your frequency is 0, then you have just a steady case. And so the lower our frequency is, the more we approach that steady case. Okay. Okay. And what do we know about the velocity profile under steady conditions? We know that it looks like a parabola. And so under low frequency situations, we should be able to see our parabolic profile for the most part. Okay. Right. And so you might see a situation that looks like this. And so we might start out, maybe we start with a full force flow like this. Okay. Then as time goes on, eventually this is going to reverse, right? Eventually that's going to go to the other side because of the oscillation, right? But then as time goes on, you might see a situation that looks like this, okay? And then you might see a situation that looks like this. Okay? And then at the next time step, it might look something like this, okay? Right? Eventually, up until, you have kind of full reversal. And so, I kind of, well, I guess I could do this. I guess I can't. Whatever. Okay. And so eventually you're going to get full reversal. And so you're going to get a parabolic profile the other way. Okay. As the pressure kind of swings in the opposite direction, the parabola is going to go on the other side. Okay. Right. And so what you see is this kind of parabola that kind of grows in one direction and then it's going to shrink and then grow in the other direction. Right. Just like my little water bending avatar last night bender thing right here. Right. And so you'll definitely see the parabola kind of react to the flow because it's going to change direction, according to the forcing, but it's still going to retain that parabola shape. Okay, and that's what happens when the frequency is low. Okay. And so there's a more physical reason why, why that happens. This may not be a very exciting result, right? We did all that work with the Bessel functions, and we still end up with the parabolic profile, right? There's a very good physical reason of why this happens, but to kind of explain that, we have to look at the high frequency case first. Okay? But I will leave you with this one piece of information that'll make more sense as we go to the high frequency case. Okay? And so when the frequency is low, when the frequency is low, we could say that the changes that are happening very slowly, right? Okay. And when things occur slowly, it gives people time to react, right? In general. And so the fluid is no different. And so what we can say is that when the frequency is low, then the flow can react to the changes in the pressure gradient. Okay. Okay. And by fully reacting, then we get our parabolic profile that we see there. Okay. Any questions on this? Okay. Okay, so let's see what happens when the frequency is higher. Okay. And so in high frequency, let's first draw, what that looks like, right? And so under a high frequency case, you might have a sine wave that looks like this, right? And so it oscillates kind of very, very rapidly. Okay. So we have rapid oscillations. Okay. So that's just a generic sine wave, under high frequency. Okay. And so our changes are going to occur a lot faster. And so what does this do for our velocity profile? Okay. Let me do this. Let me draw it in the middle here. Okay. And so let's actually assume that we start with the parabolic profile, right? So let's assume that we start, with this. Okay. Okay. Right, and so let's say at the beginning the pressure gradient is going from left to right. Okay. Right, and so if the pressure gradient is going from left to right, it's going to push the flow in that direction, right? And so that makes sense that we have a profile in that direction. Okay. But then all of a sudden, because we have a rapid change, the pressure gradient is going to all of a sudden flip to the other direction. Okay. And so with the pressure gradient going the opposite direction, eventually the flow is going to want to go in that direction as well, but it doesn't all happen simultaneously, right? And so what happens, and so what you'll see happen is that the first place where the flow is going to react is actually going to be in the middle of the vessel. Okay? And so what you'll see is that the velocity profile kind of forms this like dimple kind of, right? And so right after the change occurs, you might have see something that looks like this. Okay. Where the profile still looks parabolic going from left to right at the kind of near the walls, but the middle here starts to react, right? Because you kind of see this dimple form, right? Then as time goes on, this dimple is going to grow. And so we move on to the next time step, okay, or the next snapshot. It might look something like this. Okay. We move on to the next time step, it might look something like this. That's not a good. Okay. And so eventually the whole thing is going to change, right? Eventually it's gonna start going from right to left, but the change is happening so fast that a lot of the flow can't react. Okay. And the reason we have this is because because the fluid has mass, by definition, it also has inertia. Okay. Right. Right. So anything that has mass will have inertia. And what do we know about inertia? We know that if an object has inertia, right, if it's in motion, right, if it's already in motion, it's going to take a lot of work in order for it to change its direction. Okay. right? So think of like a solid object, right? So think of like a car, okay? And so, let's say that your car broke down because gas is too expensive right now, okay? And so you need to push it to the gas station, right? So you and all your buddies get out the car and they start pushing it, right? It takes a while, right? Unless you guys have a car of all Arnold Schwarzeneggers, right? It takes you a while to get the car going to start pushing it down the road to the gas station, right? That's because the car has inertia, and so if the car was at rest, then it's going to want to stay at rest, and so it takes a lot of work from people pushing it, to get it moving. Okay? On the flip side, if something is already in motion, it takes a lot of force to kind of stop it from moving, right? And so I think everyone's kind of familiar with that superhero cliche of like, a car is kind of barreling down the freeway, it's about to hit like a big building or something like that, and Superman comes in and just like stops it with his hand, right? It's a big deal because that car just has so much momentum that it takes a large force to stop it, right? And so fluid is the same way. So if you make these changes so fast, because the fluid has inertia, it's not going to have enough time to react. And so that's why you get these kind of weird velocity profiles, right? The ones with the dimple. Okay. And so remember what we said at the beginning of class today, that the frequency is playing a role, or it has an effect on the shape. Okay. And this is how it has that shape, or this is how it plays that role. And so the higher frequency, the more rapid the change is going to be, then it's going to have more an effect on the profile. Right? Or in other words, the higher frequency, the more it departs from that parabolic shape. All right, so next I'm going to show you the Matlab script. It's a very simple Matlab script. It's meant to just be something you can play around with, but I do want to show you what this how this effect occurs. Before I do that, are there any questions on this? Okay, all right. So let's look at that. Let's look at that Matlab script. Okay. All right. So here, if you go to the course website, so that's the entirety of the script. It's very short. Okay. And so you can see it's the extra file that I've uploaded for this week. Okay. All right. So let's look at this code right here. Right. And so the only thing that I want you to change here is this frequency, okay? And so let's start with something that's really low. And so let's start with the frequency of like, let's say 1, okay? So if we run it with a frequency of 1, right? So this would be our low frequency case. And so we would expect the velocity profiles to look pretty parabolic, okay? And that's exactly what you see. And so, under a very low frequency, we can see we have this nice parabolic shape, but it's changing with time, right? And so it's starting out, very high, and then, it's coming down as the frequency is, as it's pulled the other way, right? We can increase this a bit too, just so you can see it a bit. So I think we can increase it to 5, should still be okay. Right, and so as we increase it to 5, you can see the full kind of spectrum here. And so, we start with we start with a parabolic profile facing completely to the right, right? And then as time goes on, then the profile, goes to the left. Well, you can see we mostly have a parabolic profile here, although, we're starting to see a little bit of that effect that I told you about earlier, right? As we have kind of a profile here that kind of looks like it has a dimple. And so let's increase this even further. So let's increase this to a frequency of 10. Okay, then you can really start to see, those abnormal shapes. Okay. All right. So for a velocity profile of 10, and but what the colors represent here are different snapshots in time, right? And so in reality, what's happening is the velocity is kind of oscillating kind of back and forth. Okay, and I'm just taking kind of snapshots at fixed times. Right? And so you can see even with a frequency of 10, right, you still see some parabolicness here, okay, but you start to see more of these kind of abnormal profiles forming. Okay, and that's because the frequency is getting higher. And so let's increase this again. So let's increase it to 25. Okay,
right? So now you're seeing a lot more of these profiles, right? Because now with the frequency of 25, the pressure gradient is oscillating kind of pretty quickly like this, right? And so the flow is not being given any time to respond. And so that's why we have all these kind of intermediate profiles. But for the large part, once we reach the extremes, we still have a parabolic profile there. So, let's see what happens when we increase this even further. Okay. And so with a frequency of 50, you can see that the parabolic profile never really gets a chance to develop, right? Because the flow is oscillating so quickly that it's just having trouble just keeping up with that oscillation, right? And so that's why you see, these strange profiles like here. Just for fun, let's pick it up one more notch. Let's see what happens when a frequency of 100. Okay. And so with the frequency of 100, we see this kind of even more, right? And so you never really see, the middle of the flow develop at all, because it's just trying to play catch up this entire time. Okay. All right. And so, I posted that script for you, and so you can go ahead and play around with it, right? There's nothing, there's nothing too crazy here. I basically just took our solution and plotted it in Matlab. Okay. And so you can see, if you're curious to see how to summon the Bessel function in Matlab, this is the function right here, called Bessel J. Okay. Any questions on this? Okay. Okay, so let me go ahead and stop. Let's come back to the iPad. Oops. Okay. And so that's our velocity profile, right? And so that's kind of a good a good way to kind of illustrate how these velocity profiles are affected by the frequency. Okay. But on that same note, we can kind of characterize it even further by introducing something called the Waterslide number. Okay. Oh, by the way, I should have mentioned it before. This profile that we looked at here, it has a special name, and so this combination of Bessel functions and the oscillating part with time, this is attributed to a scientist named Waterslide. So this is known as the Waterslide solution. Okay. And so along that same profile, Waterslide kind of did a bit more work analyzing his solution. Okay. And he came up with this non-dimensional number called the Waterslide number. And so the Waterslide number is a non-dimensional number that characterizes the the unsteady nature of this oscillating flow. Okay. And so, I know, a lot of you guys are seniors or grad students, and so that engineers, scientists, we love our non-dimensional numbers. Okay, and this is no exception. It's not as famous as, say, like the Reynolds number or anything like that, but it's pretty good. Okay, to have a whole number named after yourself is something that's really cool. Okay, so the definition of the Waterslide number is the following. So actually, we usually define it as alpha squared. Okay, so alpha is the Waterslide number. And we usually define it as alpha squared just to avoid any square roots, because square roots are kind of ugly, okay? And so the Waterslide number is given by omega, right? So omega is our oscillation frequency multiplied by the radius of the vessel squared, okay, divided by the density, or excuse me, the viscosity. And so you can check the dimensions on that, right? So the frequency has units of 1 over time. The radius, of course, has units in length. And so on top right there, we have units of meter square over second, or time, length squared over time. And then the units for kinematic viscosity are meter squared over time. Okay? And so all the units cancel out, and then we end up with a non-dimensional number. Okay? All right, and just like every non-dimensional number, you know, it actually has a physical interpretation. Okay, and so most non-dimensional numbers that you see in practice, they represent a ratio of some kind, right? And so if you think of the Reynolds number is the ratio of inertial forces and viscous forces. Okay, that's probably the most famous one. And so the Waterslide number is no different. And so the Waterslide number represents transient. It's the ratio of oscillating inertial forces and then in the denominator here, because we have the viscosity, we have viscous forces. Okay. Okay. So actually, you know, very similar to the Reynolds number. So Reynolds number is just inertial forces in general divided by viscous forces. And so the Waterslide number is kind of a spin off this. And so instead of just regular inertial forces, this is, you know, oscillating ones. Okay. Okay. And so, you know, if you look back at our Waterslide solution, you know, what we can actually formulate the solution in terms of this quantity. Okay. And in fact, you know, you can make some conclusions, or you can make some, or not conclusions, you can make some predictions of what the velocity profile looks like depending on the Waterslide number. And so this should give you some more, I'd say, concrete guidance on, you know, what the velocity profiles are going to look like. Okay, because, you know, we've, you know, up to this point we've defined the different velocity profiles, but we've only defined them in terms of regimes, right? And so we said we have a high frequency regime and a low frequency regime. Okay, so let's put some more numbers on this so you can kind of see, you know, how they affect. All right, so let's first look at a situation when we have a relatively low Waterslide number. Okay, and so let's say that we have alpha squared either less than 1 or less than or equal to 1. Okay. And so if our Waterslide number is around 1, okay, or if it's less than 1, what we could say is that the ratio of the oscillating inertial forces and the viscous forces are kind of around the same magnitude. Okay. Right, and so if the viscous forces are about the same strength, or about the same magnitude as the oscillating forces, you know, this is kind of the same thing as our low frequency regime that we saw above. Okay, and so in these situations, a parabolic profile is expected to develop. Okay. And so in this case, you know, the fluid itself has is able to react to all the oscillating changes. Okay.
Okay. So visually, it might look something like this. And so inside a vessel, you have a profile, and maybe it goes the other way, right? But it all looks parabolic. And so when the Waterslide number is low, that's basically our low frequency case. Okay. And so this gives a little bit more nuance. It gives a little bit more context about, what does it mean to actually be low frequency for these cases. Okay. Right. And so if we look at the Waterslide number again, right? So Waterslide number is defined as omega r squared divided by nu. Okay. Right. Of course, if the frequency is low, then the Waterslide number, of course, is going to be low as well, right? Right. And so we've seen that, right? And so we've seen that when our frequency is low, then our velocity profile looks parabolic, right? But there's some other factors here as well, right? And so let's say that we still have a relatively low frequency. And so let's say we have a frequency of, let's say 1. We'll put a number on it. Okay? But let's pretend that we're doing this for a massive vessel, right? And so we're doing it for like a wind chamber. Okay? And so, in that case, we have a very large radius. Okay. Right. And so you're thinking, maybe you're in one of those massive wind tunnels that they have at Boeing and NASA, things like that. Okay. Right. And so if your radius is massive, right, it doesn't really matter what your frequency is. Unless the frequency is 0, then you're still going to end up with a very large Waterslide number. Okay. And so, under those conditions, even if you have a fairly modest or fairly low frequency, you're still not going to expect to see parabolic flow, because your radius is so massive. Okay. Right. And of course, we see one other factor here, which is the viscosity. Right. And so the viscosity kind of acts like to oppose the frequency as well. Okay. And so if you have a high viscosity, then what that can do is that can counteract a high frequency, right? Okay. And so if you have a fluid that's very highly viscous, and so let's say that, I always use honey just because it's the most viscous thing I can think of. And so if you have a tube of honey, right, even if you apply like a very quick, very rapidly oscillating forcing to it, you could probably still expect to see a parabola form, because the viscosity is so high, right? And so, whether your profile is going to end up parabolic or if it's going to end up with that weird dimple, it depends on a lot more than just the frequency. And so it depends on all of these factors. It depends on how big your vessel is, how big your tube is, but it also depends on the viscosity as well. Okay. And so changes in one area can be compensated by changes in another area. Okay? That's the whole idea with non-dimensional numbers. Okay. Any questions on this? Okay. And so that's the low Waterslide number case. And of course, for the sake of completeness, we can look at high Waterslide number as well. Right. And so, there's no strict cutoff. And so, I know that there's a gap here. And so I say Waterslide number less than 1. And so here I say Waterslide number greater than 10, right? But, there's a spectrum. But Waterslide number greater than 10, this is when we start to say that the oscillatory inertia forces start to take over.
And so in those situations, the flow is not going to react fast enough. And we've already seen what that looks like, right? And so we've seen that it looks like, we have velocity profiles that look like this, right? Right. And so we get these kind of funky looking profiles, right? Okay. But we always can see that there's other ways to achieve this, right? And so, let's look at the opposite end of the spectrum. So let's consider a fluid with very low viscosity. Let's think of like air or something like that, right? And so for air, because the viscosity is so low, unless you have perfectly steady conditions, it's very, very rare for you to see a very perfect velocity profile, parabolic profile for air, because its viscosity is so low, and any change that you make, the air is just not going to be able to react to time because its viscosity is so low. Okay. Okay. And so, how does this relate to the cardiovascular system? And so, you guys are working pretty hard on your projects. And so, I think at this point, you already have seen that there's a variety of different blood vessels that occur inside the human body. Okay. Okay. What's interesting about cardiovascular flow is that for the most part, unless you're running a marathon or you're about to, fight a guy that's twice your size, right? Your heart rate is going to stay relatively constant. Okay. And so the frequency is fairly constant for most people. And so the primary determining factor, whether you have a parabolic profile or not, actually depends on the size of the vessel, right? Because all your blood's mostly the same too. And so your viscosity is going to be relatively constant. Okay. Okay. And so here's some numbers to kind of give you a sense of what kinds of Waterslide numbers you expect to kind of see. Okay. And so the biggest vessels that you have in your body, or the two biggest vessels, are going to be your aorta. Okay. So a lot of you are doing the aorta or the aorta femoral models for your project, or the main pulmonary trunk. And so a few guys are doing pulmonaries as well. Okay. And so in these vessels, based on their size, you typically see Waterslide number around 13 to 15. Okay. Of course, there's variance, but that's generally the range that they kind of hover around on average for the average person. Okay. Okay. On the other hand, if you look at some of the smaller vessels, and so these are like your capillaries or these like your arterioles, those are so small that the Waterslide number for those ones end up being around 0.0 something. Okay. Okay. And so what does this tell us? And so this tells us that for some of the bigger vessels, like the aorta and the pulmonary trunk, you actually very rarely see parabolic flow in these vessels. Okay. It's actually a pretty decent topic of debate in the community around this technology, because and so you guys will see. And so, after this week, I think next week we'll spend talking about CFD. And then after that, you'll be running simulations on your models. One of the assumptions that you're going to have to make in your CFD is what does the velocity profile look like, right? And one option that, that is available is a parabolic velocity profile, okay? But, if you're running a simulation on the aorta, is it actually appropriate to put a parabolic profile on there? And so that's actually been debated quite a bit. And it affects the solution. It affects, what you get for your wall shear stress and whatnot. So, it has an impact, and so what the best velocity profile to use in those situations is still, I would say it's still kind of, it's still, we haven't really decided yet. Okay. Any questions on any of this? Okay. All right, so let's go ahead and move on to the next topic. Okay. And that has to do with the fact, having to do with the fact of the assumption of an oscillating profile. Okay. And so this is called generalized velocity time series. And so up to this point, we've kind of made the assumption that our forcing is a sinusoid, right? Okay. Right, and so we're making the assumption that our blood pressure kind of goes just like a sine wave in time. Okay. But we know that's not true, right? And so the human heart has no idea of what high school mathematics is like, and so you tell it to be a sine wave, and it looks at you like you're crazy, right? And so the heart kind of does its own thing. We know it's a periodic function, but it doesn't really look anything like a sine wave, right? We've already seen what the pressure profile looks like. Okay? When we did our unit on arterial biomechanics. Okay? And so we know that the pressure looks something like this, right? So we come up when the heart is pumping, and we come down. We have this little tiny notch thing. Okay, and it comes down just like that. Okay, so we have a pumping period, we have a relaxation period, and we have our little tiny notch. And so eventually, this is going to repeat, okay? But this looks nothing like a sinusoid, right? It looks like a a bike hill that you're going to bike down and break your neck on, right? The mountain, yeah, there you go. That's the word I was looking for. And so, the fair question to ask is that, if we spend all this work developing this solution for a sinusoid, but how valid is it actually for the human body, when our pressures we know are not going to vary like a sinusoid, okay? But, we're in luck, yeah, because sinusoids are actually a great thing to put your solution in terms of, because we know that there is a mathematical tool out there called Fourier Series, okay? And so with the Fourier series, we're able to reconstruct any functional form as an infinite sum of sinusoids. Okay? Okay. And so mathematically, it looks like this, right? And so before, what we said was our pressure gradient here, partial P partial Z was equal to A e to the I omega t. Okay. And so what we said was it was a sinusoid with a fixed frequency. Okay. But what if we modify this so that instead of being a single sinusoid, it's actually an infinite sum, or we can truncate it. So we'll say it's a finite sum of these sinusoids. Okay. And so what if we say instead, this is a summation, okay, where middle n starts at 1, it goes up to some number big N, okay. And now the omegas and now the coefficients are functions of that n as well. Okay. Right, so this is great. And so, even though we've added this summation here, the general functional form of our pressure gradient has not changed. Okay. Okay. Right. We're also blessed with the fact that the differential equation that we solved before, right? The differential equation that we solved before, the Bessel's equation, was a linear equation. Right? Okay. And so what that means is that we actually don't really have to do much to modify our solution. Okay. And so what you'll see is that the very general Bessel equation solution, or the Walmersley solution, excuse me, the most general one is not just that one function that I showed you, but it's actually a summation of different functions. Okay. And so the general Walmersley solution is given by the following. So we have uz as a function of r and t is equal to summation, okay, n is equal to 1 to big N. Okay. I'll define big N in a second. And then we just have our regular solution. Okay. And so this is all just going to be repeat from before. Except, whenever we see omega, I'm going to put a subscript there, omega n. Okay, and our a here turns into an as well. And so this right here is our general Walmersley solution.
And so of course, you know, the two terms here that kind of stick out, or the two variables, one of them is n, of course, and the other is a, right? And so we've had a in our solution this whole time, you know, but we haven't really defined what that is, right? And so we've kind of just been using it. It's not the cross-sectional area, and so it's not that a, okay? And so now that we've kind of put this equation, we put the solution in terms of the Fourier series, the a kind of develops its, you know, its stronger meaning, okay? And so let's start with that. And so what the a here represents the magnitude of that matching sinusoidal wave. Okay? Okay. Right, and so when you make the Fourier series, you know, if you've seen Fourier series before in a previous class, you know, maybe you've seen it in 308, right? Part of what makes the Fourier series work is that each of the sinusoids have a different magnitude, right? And when you add together those sinusoids of different magnitudes, you know, that lets you kind of recreate any periodic function there is out there, okay? And so that a end is kind of you can kind of almost think of it as a lever, or kind of a way to basically make sure that our solution can adapt to any periodic function. All right, and so big N here represents what's called the cutoff Fourier mode. Okay. Right, and so if you want to look at the pure, you know, the pure Fourier theory, you know, the pure Fourier theory says that this summation should actually be infinite, right? And so we should continue summing terms over to infinity. And so if you make that infinity, then, you know, then really you can make any function, right? But in reality, you know, ain't nobody got time for an infinite sum, right? And so we have to cut it off at some point. And so what we can say is that, you know, we can retain enough accuracy by choosing a cutoff frequency that's high enough, okay? Okay. And as to, you know, what's a good cutoff frequency? Well, it depends on the situation. But for cardiovascular flows, usually, you know, in my notes here I have 10, you know, but most of the time, you know, even just like 4 or 5 modes is usually more than enough. Okay. So I'll say n is equal to 4, from anywhere between 4 and 10. That's usually a good number for cardiovascular flows. And so with the Fourier series, you know, we can generalize this profile to fit with any kind of pressure waveform. Okay. And that's really powerful because, you know, it's you know, every person has kind of a different pressure waveform. You know, it really depends on, you know, what that person, what their overall health is like, and what their, you know, how big they are and how big their vessels are, right? And so to have a solution here that can automatically kind of adapt to, you know, every person's own anatomy is really powerful. And so we can use this to kind of give a good estimate of what the velocity profile looks like. Okay. All right, any questions on this? Okay, one last thing I want to go over. This is going to be really fast. Okay. Remember, you know, one of the reasons we started going down this path of the velocity profile was that we wanted to find a way to compute the wall shear stress, right? So let's talk about that very briefly.
Okay. Right, so this is the first time that we're able to compute this, right? And so because in order to compute the wall shear stress, you kind of need the velocity profile. Because the formula for wall shear stress looks like the following. And so we have TW is equal to mu partial UZ partial R. Okay. And if you want to compute this at the wall, then you plug in R is equal to big R after you've taken the derivative. Okay. And so what this term here basically says is that, in order to compute wall shear stress, we need to take the derivative of our Waterslide solution with respect to R. Okay. And so this solution that we have up here, right? So you can do the most general one, or you can do the one for the single sinusoid. We have to take the derivative of this with respect to R. Okay, and it's not as bad as you think, because the only term here that actually has little r is this one right here. Okay, everything else is a constant, and so we can just take them out of the derivative. Right. But in order to perform that derivative, you need to know how to derive the Bessel function. Okay. Right, and so if you take partial r of J0, and let's say that J0 is just a function of r, okay, what you get is this. Okay, and so we end up with J1. And so J1, this is the Bessel function 1 of first order. And so the Bessel functions that we've been working with, they're of the 0 order. So hence the 0. And again, the Bessel functions, that's not something you can evaluate by hand. But Matlab will know, and other softwares will know how to plot those things for you. All right, any final questions on this before we wrap up for the week? Okay, all right. So I did want to end a bit early today because I know people have questions on the project, and so I want to make sure I have time for that. And so if you have questions on the project, I'll be up here until 5:15, and then when the next class comes that kicks us out, I'll go back up to my office. And so if you're on Zoom, if you have questions, then when I go back to my office, let's hop on to Thursday office hour, that Zoom link, and then I'll see you there. Okay. All right, but if you don't have any questions on the project, then thank you guys for tuning in this week. Next week, next week we'll start talking about CFD, and so that's going to be really exciting. And so, make sure you come for that. And so, hope you guys have a good weekend, and I will see you guys next week. Thanks, guys. Yeah.
Yeah, I'm just
Oh.
going to turn it in.
Okay. It'll be the same as the tutorial. So you're just going to zip the whole project and then submit that zip project to Canvas.
Because when I go look at it, it says it's like the last update it's giving is from like when I first downloaded it.
Oh, okay.
But I can open it here just fine.
Okay. It might be referring to some of the older files there. Why don't you go ahead and submit that one? Then I'll go check it on my computer, and then I'll let you know if it's the most updated.
Thank you.
And just send me an email just to remind me too, because I. All right, Suba, I'll meet you on the Thursday office hours link on in my office in about maybe like 5 minutes. Okay.
Okay, yeah, no worries. Thank you.
I can't hear you because the sound is off, but I trust you said okay.